of this lecture, we'll see some quick applications of the Sylow theorems and of the material that we've discussed so far in this lecture to some problems that we've considered earlier in the course. So in lecture 13, we proved that if p less than q are primes and p does not divide q minus 1, then any group of order pq is abelian. So we're going to prove that, but we're going to prove something a little better now. Let's suppose p less than q are primes and that G is a group of order pq. We're going to name capital P to be a Sylow p subgroup and capital Q to be a Sylow q subgroup. So we're going to show that Q is always normal in G, that there's always exactly one Sylow q subgroup. And we're also going to show that if P doesn't divide Q minus 1, then P is also normal in G. So there's a unique Sylow p subgroup as well. But now we see that NP equals NQ equals 1. So by this theorem from the last video, G is isomorphic to a direct product of its Sylow p subgroups, so of its Sylow subgroups. So it's isomorphic to P cross Q. P has order P, Q has order Q. Any group of prime order is cyclic. So G is isomorphic to Z mod PZ cross Z mod QZ. And that's isomorphic to Z mod PQZ because, for example, 1, 1 is an element of order PQ in this direct product. That in Z mod AZ cross Z mod BZ, the order of 1, 1 is the LCM of A and B. And because P and Q are relatively prime, that is the product. So what are we seeing? We're seeing that any group of order PQ is abelian when P does not divide Q minus 1. But we're also seeing that even when P does divide Q minus 1, we still have a normal Sylow q subgroup. OK, so the proof is going to be a straightforward application of the third part of Sylow's theorem. So what do we know about the number of Sylow q subgroups? Well, it's congruent to 1 mod q, and it divides P, right? It divides the order of G divided by Q. So that means that it's either 1 or P, because P is a prime. But P is less than Q, so it's not possible for NQ to be equal to P, because that means P would have to be congruent to 1 mod Q, but that's not possible because P is a prime that's less than Q, right? Q does not divide P minus 1. So that means NQ equals 1, and having a unique Sylow q subgroup is the same thing as saying that that Sylow q subgroup is a normal subgroup of G. So let's do the next part. What do we know about the number of Sylow p subgroups? Well, it's 1 mod P, and it divides Q. It divides the order of G divided by the highest power of P dividing the order of G. So it's either 1 or it's Q. If it's Q, that means that Q is congruent to 1 mod P. But that exactly means that P divides Q minus 1. So if P doesn't divide Q minus 1, then NP equals 1 also. OK, so let me just make a remark. If P does divide Q minus 1, then we know that we have a Sylow q subgroup that's normal. But maybe NP is actually equal to Q, and the Sylow p subgroups are not normal. So we'll see a little bit later in the course, a couple lectures from now, that that is possible. That when P divides Q minus 1, there is a non-abelian group of order PQ. There's exactly one isomorphism class of a non-abelian group of order PQ. So like, for example, where P divides Q minus 1, you could take P equals 2 and Q equals 3. So 2 divides 3 minus 1. There really is a non-abelian group of order 6, but there is exactly one non-abelian group of order 6 up to isomorphism, and that is S3. So I'll pause and erase, and then we'll see one more application of the Sylow material that we've seen so far that is related to a problem that we also thought about in lecture 13. In lecture 13, we proved that if G is a group of order 45 and G has a normal subgroup P of order 9, then G is abelian. So now we'll prove something better. We'll say that every group of order 45 is abelian. Moreover, we'll be able to classify them. that every group of order 45 is either isomorphic to z mod 9z cross z mod 5z, or is isomorphic to z mod 3z cross z mod 3z cross z mod 5z. We're going to see this as a straightforward application of Sylow 3. What do we know about the number of Sylow 3 subgroups? Well, it's 1 mod 3, and it divides 5. It divides 45 over 9, which is 5. So if you think about it, since 5 is 2 mod 3, that means n3 is 1. So there's a unique Sylow 3 subgroup. Sylow 3 subgroup has order 9. We know there is one, and it's normal. So OK, using this result from before, we could say that G is abelian. But I don't want to do it that way. I want to now look at the other Sylow subgroup. Let's look at the number of Sylow 5 subgroups. Well, what do we know? This is 1 mod 5, and it divides 9. But the only thing that's 1 mod 5 and divides 9 is 1. So n5 equals 1. There's a unique Sylow 5 subgroup as well. But we saw that in the case that for every prime dividing the order of the group, there's a unique Sylow p subgroup of that order. That means that your group is isomorphic to a direct product of its Sylow p subgroups. So let's name these Sylow p subgroups. Let's say p is the Sylow 3 subgroup, q is the Sylow 5 subgroup. And this theorem that we proved shows that G is isomorphic to p cross q. OK, how do we do this second classification part? Well, we proved earlier that if you have a group of order p squared, it's either isomorphic to z mod p squared z or z mod pz cross z mod pz. These groups are clearly not isomorphic to each other. One is cyclic, the other is not. So that means this subgroup P, this normal Sylow 3 subgroup, is either isomorphic to z mod 9z or z mod 3z cross z mod 3z. The Sylow 5 subgroup has order 5, and every group of order 5 is cyclic. So every group of prime order is cyclic. So that's it. So now we just use the fact that we know G is isomorphic to P cross Q to say what G could be isomorphic to. So let me just say, what is 45? It's P squared times Q. So this argument that we just gave is not unique to order 45. You could check that it shows a really similar result for any group of order P squared times Q, where P is less than Q or primes, and P does not divide Q minus 1. And we'll say more about groups of order P squared Q in the next lecture.